Okay, hello. My name is Gordon, and this is a recording of the first part of the my demo for at the Machine Learning Workshop at North American Solid State Chemistry Conference 2023, talking about active learning with Gaussian process regression. This notebook is available in its entirety at my GitHub page, which is here, github.com/gp0942/NASSCC2023-ML-workshop. There are two options there. There's either this one, which is for the Jupyter notebook, or there's one there that I've optimized for Google Colab. And so you can use whichever one works better for you. So the goals of this demo today, for part one, are learning what is Gaussian processes, and that sort of means what are kernels, what are prior and posterior distributions, as well as what is active learning and how can we use active learning to make better choices in our experimental design over random guessing, and how acquisition functions and a few different examples of acquisition functions play into this. And then also touching on exploration versus exploitation and what that means. So to run this notebook, you need some pretty simple, if you're running it on Jupyter Lab, if you're running it in Colab, everything should be already installed. If you're running it in Jupyter, you'll need some pretty simple notebooks. Mostly, probably the only one you might have to really install would be scikit-learn, maybe matplotlib, but pandas, numpy, scikit-learn, matplotlib, scipy, and math should be the only notebooks that you should need for this. Actually, I don't even think we need pandas. Okay, so we'll run that cell. If you are trying to remember how to run cells, it's either Shift-Enter or Control-Enter, depending on if you want your key to move to the next cell automatically. So I'm going to Shift-Enter. That will import the libraries. Once this little asterisk goes away, that means I am done importing the libraries. So to start off with, we're going to just think about what a machine learning algorithm really does. And so machine learning is designed to model data. And so we want to think about two things, which is what is the data we know and what is the data we want to know. So let's first think about data that we want to know, but let's think about the most simple function we could possibly have. So here I'm just going to define a simple linear function. So I've got y equals 0.004 times x minus half. And so I chose a couple coefficients here, just you'll see why when we actually plot this for x values ranging 0 to 300. So all this cell is going to do is calculate my values of x from 0 to 300 in integer steps, and then calculate y values for each of those x values based on this function that I've set up here. Okay, and so we're going to call this our ground truth, right? This is what is actually happening for all values of x. If we had perfect knowledge, we would know this function, but as we are experimentalists, we don't know the function that controls our property or whatever it is based on our observable input, maybe the composition or something like that. But okay, we can plot that f of x to see what it looks like. And of course, it looks like a line ranging from about -0.5 to about a little over plus 0.6 along our scale of 0 to 300 for x. But as I mentioned before, this is what we don't know, right? We don't know the underlying ground truth function here. We only know a few samples, right? We have a certain number of compounds that we have made and measured in the lab, and that's the information we have to go on, and we're using machine learning to try to interpolate and extract information from what we do know about what we maybe don't know. So to get to that idea, what I've done here in this cell is we set a number of known samples. And this is a number you can change if you want to when you're going around and playing with this notebook. Change it to be whatever you want. I set it to 5. So I'm going to say we know 5 samples ahead of time. And if I just pick 5 random points along this line and plot that, these are maybe the 5 points that I know. So one of the utilities of machine learning is saying from these 5 points, can I try to understand the relationship in between in my gaps in knowledge, right? And hopefully, because this is such a simple function, we're going to see that it actually does a very, very easy job of this. Obviously, in the real world, functions are not so simple as linear dependencies, at least usually, for things that are interesting. So What we're going to do next is define the architecture of our machine learning model. And what that means is defining the math for how the machine learning model updates itself and tries to fit to the data. And here I'm going to use two terms, one of which is a kernel. And the kernel is more or less a algorithm that the model will use as a way to update itself as we train it. And I know that that's pretty ambiguous, and that's okay. It's not really that important to understand how the kernel is working or what that function looks like. If you want to look more into that, the kernel I'm specifically looking at here is this radial basis function. It's a pretty simple one that goes with the Gaussian process regressor. And there's some links here that explain a little bit more about kernels and Gaussian process regressors. I'm choosing Gaussian process regressor here for a couple reasons. Gaussian process regressors are really good for very, very sparse data sets, meaning we have not many known measured values among a large area of unknowns. And that's often the reality in materials science and exploring solid state chemistry, because we have so many different elements and compositions we can work with. And also because Gaussian process regressors as a regression type model give us a predicted number if we're, for example, interested in the property prediction, but they also give us a standard deviation on that measurement. And that will be really helpful for doing active learning, as we'll see when we get a little later. So I'm defining the kernel as my radial basis function, and there's lots of hyperparameters and things that I could change and mess around with here, but I'm just going to do the most basic one I can. And then I define my Gaussian process model, I call it GP here, as Gaussian process regressor, define the kernel, and then this n-restarts optimizer just helps it stop crashing. But there's lots of other, again, hyperparameters that you could go through and optimize if you were trying to make the best model you possibly could. But for the sake of this demo, I think we can just stick with the simplest thing we can. So I'm going to run this cell. That's now defined my model, but what it hasn't done yet is given it any data. So my model has been instantiated, it exists now, but it hasn't gotten any of the information about our data. So I'm going to be a little cheeky, and I'm going to, before I give it that information and let it actually train and do what we call fit the model, I'm going to give it all of our predicted, all of our x values and have it try to predict our y value based on that. And so, of course, this is kind of nonsensical because our model has no information, so it's going to make bad predictions. But this will just give us a sense of what the model's distribution looks like before we've given it any information at all. So if we plot this, you'll see, okay, the way that our kernel and our Gaussian process regressor is set up is when it doesn't know anything, it just defaults to predict the y value of 0 with a standard deviation of 1. So here, my dashed line in red is my average prediction, or my predicted value, and my the shaded area here is the standard deviation of that prediction. So not very good prediction, but of course it's not because I didn't actually give it any information. I didn't train it on any of my known data. So next what I'm going to do is train my Gaussian process model just on my known data points, and that's again just those 5 data points that we actually have here along this curve, and we'll see how it does. So this would be called my prior distribution, and when we train it and then plot it again, this is going to be called our posterior distribution, and so we can compare these two. And what we see is, mostly because this is such a simple function that we've given it, it does a very, very good job and fits it right on with no real uncertainty. It feels very confident in this guess, and that's because our model is just a line. So great. But this is not the reality of most real-life functions. We have more complex functions. This was just meant to illustrate how prior and posterior distributions will look. Okay, what about more complex functions? Well, if we start with a different function instead, so now I'm going to define my f of x to be different. And we have a couple different options here. I'm actually going to choose this first one, but you can definitely write your own function here as well. It's just really all I did was a combination of sines, cosines, Gaussian style exponentials, and kind of sum those up. And again, this will just calculate my x, or take my x values from 0 to 300 and calculate my y values based on that. And if I plot that, we'll see what this function looks like. Okay, so this is a little more, at least in terms of a one-dimensional problem a little more complex, right? We've got some local maxima, some global maxima that are near some global minima, and lots of little waves and bumps and things along the way. But we're imagining that we're trying to maximize this y value through whatever our process is. Let's call it trying to maximize the temperature for critical superconducting temperature, or trying to maximize magnetic moment, or whatever physical materials property we're trying to maximize. We're trying to get to this peak in the global maximum. And so there's a few ways we can go about that, right? And one of the worst ways we could go about that would be to make random guesses along this curve. Well, actually, sorry, let me back up a minute. This is our ground truth again. And so again, we have some data going into this. So here is if I just do this exact same thing and give us 5 known data points, here's our 5 known data points along this line, just that I chose totally randomly. And so that's going to give us a little bit of information about what's going on here, but less than it did probably for the linear function, because there's a more complicated relationship here. So doing the exact same thing again, I'm just going to instantiate my model. I'm going to give a prior distribution, which again doesn't have any idea what's going on. It's just predicting 0 with a standard deviation of 1. And then I'm going to train my model on these known data points, these 5 points here. And let's see how it does this time. Okay, so now this is a little more interesting. Because you can see the standard deviation of our model changes dramatically based on how close it is to other known data points. It's tried to fit a curve that passes through all these data points, so that's great. And the standard deviation of that prediction varies the further away we get from these predicted values. So when we have more of them close together, it doesn't think that there's very much standard deviation there, but in these gaps in the middle, it thinks, I don't really know, and over here I don't really know, and over here I don't really know. So as we're trying to work towards finding this global maximum, we can think about different strategies, like I was saying before, for getting there. One of the worst strategies we could take is to add more points randomly, because that is just going to not really give us, that's not a systematic approach, that's just throwing darts at a dartboard. And so that is going to be wasteful if we have expensive experimental design, or even computational hours that are getting burned just looking through a massive design space randomly. So we can see how well this does, and I can just give you an example. So here in this cell, the parameter you can play with is this n loops. This is going to tell you basically how many points to add each time. If you say 10, then it'll loop through 10 times, it'll add a point, and then retrain the model, and then add another point randomly, and retrain the model, add another point, all the way up till it's added 10 points. So let's just start by adding 1 point. I don't need to explain what all this code is doing. If you want, you can go through and read all the comments on it. But essentially, it's just doing exactly that. It adds a random point, retrains the model, plots the fit, and then does it again if you ask it to. So if we do this 1 time, now we can see, okay, here's our underlying curve. Here are our original 5 known data points in black. The red dot now is the one that we added most recently. That's our randomly added point. And you can see how the fit of the model has changed when we've added that point. It went from the blue curve, it was the original curve, to now this orange curve. That maybe is a little bit better. In fact, if we look at how the RMSE here is plotted in this with this black line, the RMSE has gone down significantly, although that's almost more random luck than anything, because it kind of decided to go up rather than be way down here. And our maximum y value remains unchanged, right? It was still this one. So we haven't made any progress towards finding a improved material over the state of the art. Maybe we'll try it again with 15 loops. And all I'm going to do here is turn off the legend so that it doesn't get too crazy. If I choose 15. Okay, so now I've done this 15 times. We've added a bunch of new data points. Here's the last one we added. And actually we got kind of lucky. Randomly, we seem to have guessed very near the peak of this, although it wasn't till a while. It looks like around the 10th point that was added or so, we happened to guess at that local maximum, and so we got up to a maximum y of about 2.6 or so. And our RMSE continues to go down, of course, as we're adding more training data, but it's sort of slowly progressing, gets to a value of 0.2. So all this is to say, of course, adding new data points will be valuable, but what we want to do is think about what's the way we can add the most value with each new point that we measure. And that's the concept behind active learning. And that's what we're going to get to next. It's a smarter way to do things using our machine learning models, how they can guide our experiments, sort of working together with experiment. So the way that an active learning approach works is it essentially takes what we've got and uses something called an acquisition function to decide what are the best new points to measure, rather than measuring randomly. So I'm just going to reset my model here. This just fits it back on our original 5 known data points and resets our y values and everything. And so there's a few different acquisition functions that are common to use, and we're going to talk about a few of those, but you could also really imagine using anything that might seem suitable to your problem, right? If you're the chemist and you know what makes sense in your particular case, what you're trying to optimize and how the model should be choosing a new point that is the most valuable, then you can design your own acquisition function that encapsulates that physical concept. So one of the most simple ways we could do this is by combining together is through what's called upper confidence bound. And we do this by combining together our predicted value with our standard deviation. And so that's, you can see in this equation here, my upper confidence bound value is going to be, for a particular point I, is going to be the predicted value at that point I, that's what this y is, plus a coefficient lambda multiplied by my standard deviation at that particular point I. And so if we look back up here, we can imagine how this would work, right? My dashed line, these are all my predicted points, y, and my standard deviation is this shading. So what it's saying is there are places where I want to, if I have a high predicted y value and also a high predicted standard deviation, that's an indication that maybe this is a place where there's a likelihood of finding a compound that exceeds our best known, right? We're improving on the state-of-the-art material. If we have a low predicted y value, even if our standard deviation is relatively high, maybe it's not going to be as likely to be a good material, and especially not if we have a low predicted value and we have a very small standard deviation. That's not going to be good. So we want areas of high uncertainty that are also predicted to be relatively favorable. So here I'm going to plot out the same distribution, but with also plotting the upper confidence bound values on top of it with 3 different values of this lambda parameter, and our lambda parameter is going to weight how much should we account for the standard deviation. So a large value of lambda means that our upper confidence bound is more skewed towards standard deviation, and that's called exploration because, again, that's going to favor areas of uncertainty and trying to find where the model is very unsure. Low sigma values or low lambda values are going to favor areas where y is very high, where our predicted value is high, and so that's called exploitation. So here I've got a few lambda values, 3, 1, and 0.2, and we can see how choosing these different values would guide our next point differently. Okay, so in dark kind of golden, this almost reddish one, I've got my highest value of lambda, that's lambda equals 3, and that's going to suggest with this red dot is telling me where the peak of that curve is. That's suggesting I measure all the way over here at x equals 300. And that's largely because we're really favoring the high standard deviation, right? So even though this is maybe not the highest point on our curve, if we were to look back here, it's not our highest predicted value because the standard deviation is so large. It's saying that's where you should make your next measurement. When we set lambda equal to 1, actually that's going to just be exactly our predicted y value plus our standard deviation. So just tracing the upper part of this red shaded region, that's going to say that the best place to go would be right between these 2 points. And if we make lambda very low with this light yellow, that's going to favor closer to our already known highest point. And so I want to make clear there's no correct choice for lambda here, right? Here we can say, oh, probably we should do this one. That's sort of getting us towards, that seems like a reasonable middle ground based on what our function looks like underneath. But we don't know what this underlying function is in real life. So we have no idea to know what lambda should look like, but that's something you can constantly change and adapt as you are going through the active learning cycle. So speaking of the active learning cycle, what this is saying then is, let's say we want to make a new measurement, and we decide on our lambda value of 1. We'd say, okay, we're going to measure now at about an x value of 120 or so. Put a new point there. It would be right on this curve right here. Then we'd retrain our model. That would give us a new fit. That would hopefully be better than the previous fit and with lower standard deviations in this area that was previously high uncertainty. Although it would be a new global maximum as far as the points we know. So we would then see where the model suggested we go next and next from there. And that should be a better than random way of approaching this problem. Okay, so that's one way, upper confidence bound, of using an acquisition function in the active learning cycle. Another way we could do it is with what we'd call probability of improvement. And that is exactly what it sounds like. It is a function that calculates what is the probability that a new prediction is going to be higher than the previously known best value. So if my model predicts that the best value across my whole search space is 100, then the probability of improvement function will calculate what is the odds that if I measure at some value, it's actually going to be higher than 100. So this all is based on the math behind the probability density distribution. This should be probability density function, and the cumulative distribution function. So this is the probability density function, and I'm just going to show here. This is what these look like. So probability density is just a Gaussian curve, and that is exactly, it's a prediction mean is at 0, standard deviation is 1, and reading across on the y-axis tells you what is the probability of measuring at that distance away from the mean. The cumulative distribution function is the integral of the probability density as you go left to right. So in total, this probability density is normalized to 1. And so as we are very, very far to the left, there's a very low density below this curve, so it's close to 0. Once we get here to the middle of our density function, the cumulative distribution is exactly 0.5, half. And then by the time we get to very high probability density value, it's sigma values towards positive standard deviations, our cumulative distribution is very, very high, close to 1, because almost 100% of the curve is going to be under 3 standard deviations, for example, above the mean. So using these two functions, specifically the cumulative distribution function, we can now see how the probability of improvement works. I know, again, this is more equations and math, but bear with me. I promise it's not that complicated. We'll walk through it. So essentially what this does is for each point I in our 0 to 300 values for x, we're calculating a z-score, which a zz here, that is the difference between the predicted value at that point and the global highest predicted value normalized by the standard deviation at that value. So it's essentially saying how many standard deviations, better or worse, is the prediction from the maximum prediction. Then we have this tunable parameter epsilon that again is going to allow us to control for exploration versus exploitation. And once we've calculated that z-score, our probability of improvement is just the cumulative distribution function of our z-score. So We're going to do exactly the same thing that I did with upper confidence bound here, where I will plot three different, our same global truth function, our same global truth, our same 5 known data points, and 3 different values of the probability of improvement based on different epsilon values. So here I've got epsilon equals 5, epsilon equals 1, and epsilon equals 0. And the way it works out is large epsilon favors exploration, small epsilon favors exploitation. So let's see how that goes. Okay, so again, and I should point out that these probability of improvements are scaled so that they all look, that we can compare them very easily, but they wouldn't all be exactly the same height. Because, yeah. Okay, so if we have a large epsilon value, again, that is favoring exploration. It's guiding us towards this point where we know less because it's furthest away from some of our data, towards the tail end where the standard deviation is the largest. A middle ground epsilon value kind of puts us in the middle here, similar spot to where we were with upper confidence bound, and a very low epsilon function of 0 puts us right next to our previously known global maximum. So very, very exploitative over what we already knew. Okay, we can improve on this just a little bit with one more tweak, and that is to change probability of improvement to expected improvement. So this adds a couple terms to that probability of improvement. We calculate the z-score in the same way, but then rather than calculating the probability of improvement, we calculate expected improvement, which rather than just saying what is the probability that our our prediction at this value will be better than the best one we already know, it's saying how much better will it be, if at all. So expected improvement could be negative or positive. Well, actually, I don't know. I don't think it can be negative. Well, regardless, expected improvement accounts for how much better is it able to be, or is our prediction likely to be better than the previously known global maximum. And so we're using a combination of the cumulative distribution function and the probability density distribution function. No, it has to be, it can only be, no, it could be negative if this is negative. So could potentially be negative. The CDF and PDF should always be positive. Okay, so we've added just a couple more things that give us a sense of, if it is better, how much better is it? Because we would rather predict, even if two things are equally likely to exceed our previously known maximum value, we would like the one that exceeds it by a lot, rather than the one that just barely exceeds it. So let's do that again, and here I'm just going to choose, again, a few epsilon values, 2, 0.1, and 0. We'll see how those compare. Can try. We can mess around with this too. Let's see if I change it to 0.5, does that give us different things? Maybe not. 0.8. And then it ends up over here. So interestingly, this actually gives us a little bit of different results from the probability of improvement, where now even with an epsilon value of 0, we are being dissuaded from picking right next to here, because even if it is likely to be better, our amount of betterness is so low compared to here because we have a larger standard deviation. So at high epsilon values, we're still over here. At low epsilon values, we're kind of predicting in the middle now. But again, go through this. You can feel free to change the epsilon values, mess around with, see where it guides you. And again, there's no right or wrong answer. In real life, you will have no idea what the correct value for epsilon is. It's just sort of choosing it based on what seems to make sense, and how much you want to explore versus how much you want to make incremental improvement. That is, but that sounds bad, but exploration is not always fruitful, whereas incremental improvement often is. So depends on what you're going for there. Okay, so now we can do essentially the same thing that we did all the way back here, where we were adding random data points and trying to improve our model. But instead, we're going to use expected improvement to do that for us. So I'm just going to do 15 new points with an epsilon value of 0.1. And let's see how well our model does in lowering the RMSE and finding that global maximum. Okay, so you can see a few things. Our final curves are actually pretty good. We've managed to sample the distribution pretty well, and especially found, most importantly, both the global, or well, the global maximum as well as this maximum here, and sort of this one over here. This graph in the middle is showing the expected improvement function. So this is saying if we were to measure another point, we would measure this point right here at around x equals 15, 20, something like that. And if you want, you can go through one by one and keep doing a new loop each time. See how where it suggests you to go with each step. And now we can look at our RMSEs. Our RMSE goes down and actually gets significantly lower than it did previously. Remember, before up above it was about 0.2, so now we've gotten down to about 0.08. That's a lot better. And more importantly, we were able to get to our global maximum, about 0.26, significantly quicker. So it looks like on step 7, I think before it was step 10, but honestly, we got lucky that it was even step 10 in the previous one. So much more quickly, we were able to hone in on where our global maxima were here. And so if you're doing experiments that are expensive in terms of time and products that are going into it, that's going to be a very valuable, it would be very valuable for you to do this kind of analysis that's telling you what is the highest value experiment. And so in part 2, this kind of concludes part 1 of this demo. In part 2, we're going to go through and look at a real life example of trying to implement active learning for the prediction of a real property based on data that I'm actually going to extract and featureize from the materials project. So I will see you back in part 2.